Alright, good afternoon everyone. Welcome to lecture 16 of BMS 300. Today we'll talk about the parts to the Skeletal system. But before we get into the materials for today, I have a couple of announcements for things coming up on Wednesday. So what's happening on Wednesday? Exam 1, yay, fantastic. So it will be in the evening from 5 to 6:50, and it will not, I believe this class is this room will be one of the places where the exam will be, but it's going to be held across 4 different rooms on campus, alright? And so I'll send an announcement saying which room you should be in based on your last name. So maybe A through K will be in one room, and then K through F, sorry, different order. They'll be in another room, right? So I'll send that announcement out. So look for that announcement, and the next thing is the exam will have, I believe, 85 points for multiple choice questions and 15 points for fill in the blanks. Alright, and so I have 35 multiple choice questions, each worth 2.5 points, and so that is, if you do the math, 35 times 2.5 is 87.5. Right, so you get 2.5 bonus points extra because of the extra question, and then I have 18 blanks for the fill in the blank, so you could get up to 18 points. So there are a few bonus questions as well. And for the fill in the blanks, I have a word bank. Alright, so you will have 15 blanks, and there are 35 words in the word bank. What that means is, if you make a spelling mistake on the fill in the blanks, we will take off points, because it just means you are not capable of looking at the word bank and writing the correct answer. Alright, so please watch the spelling since the word bank is provided. And I would highly recommend that you read the fill in the blanks without looking at the word bank. Try to fill it with the best of your knowledge, then try to jog your memory by looking at the word bank. I really think the word bank should only be for checking the spellings. I feel if you are fishing there for answers, it may not be very helpful. Alright, so those are my couple of things I wanted to say. Any questions at all before we get into today's material? Okay, just so you know, the skeletal system is not going to be there on the exam 1. That being said, there are some aspects related to the skeletal system which I discussed in the connective tissue and in the integumentary system. So that is fair game. Alright. So if you see a question on the exam which has something to do with the skeletal system, don't freak out. It is part of what you're responsible for, because it was covered in either the integumentary system or in the connective tissue. Okay. So with that said, let's jump right into today's content. So here's an overview of what we've discussed until now. We talked about classification of bones based on location, based on shape, and then based on also the internal structure of being either compact bone or spongy bone. And then we looked at the anatomy of compact versus spongy bone to see what the differences in terms of its structural unit. You have trabeculae in spongy bone, you have osteons in compact bone, and we talked about its organization. And then we moved on to the discussion on bone formation and development, and that led to us talking about intermembranous ossification and endochondrial ossification, right? And we're going to pick up where we left off, because both of those will also play a role not only in the development of the embryo, but also in the development of the fetus, but also in the development into adulthood. And then we'll talk about the functions of the skeletal system, and we'll see how the bone will repair itself after any sort of damage. And then finally we'll see pathology of 2 kinds. What happens if you have decreased bone density? That can lead to osteoporosis, which most of you should be familiar with. But we'll also see what happens if there is too much bone density, and what would be those implications as well. So let me quickly review the differences between endochondrial ossification and intermembranous ossification. So in endochondrial ossification, we find that a cartilage is going to be involved because chondrocytes are going to play a role in it. And so it will start with the mesenchymal cells differentiating into chondrocytes. And those chondrocytes, they will produce a matrix to surround it. And keep in mind that all of these chondrocytes are going to form the hyaline cartilage. So the template which will eventually turn into the bone is going to be hyaline cartilage. And in this hyaline cartilage, we see that the chondrocytes will keep multiplying, but eventually there will be calcification of the matrix, which causes the cells to die. And as the cells die, there's a cavity there, and that cavity will be invaded by blood vessels, which will bring osteogenic cells. And these osteogenic cells can convert into osteoblasts, and that can help develop the bone tissue. So this is an overview of endochondral ossification. And when we consider that and then compare it with intermembranous ossification, we see that again you start with mesenchymal cells, which will turn into osteoblasts. And those osteoblasts will start collecting in this region known as the ossification center. And that's where they will start producing the osteoid, which is the non-calcified matrix. And eventually when calcium gets integrated into the osteoid, it will cause it to get mineralized. And the osteoblasts which are trapped within that bone matrix, they will convert into osteocytes. And keep in mind that as these osteocytes are forming, they have to accommodate the blood capillaries, which were also produced by these mesenchymal cells. And so the bone will form into these short beams known as trabeculae. And that's why you have the blood capillaries and you have the spongy bone. And on the surface, however, we said that compact bone will be formed because the blood vessels aren't going to interfere with the fusion of the bone tissue which was produced in the previous steps. So on the surface you have compact bone, but in the middle you have spongy bone because of the presence of blood vessels which are intervening in a random fashion. Any questions at all? Right. So both of these steps, endochondral and intermembranous ossification, they not only play a role in the development of the fetus, but it also plays a role after birth and into development into adulthood as well. So I'll tell you where that happens. So now let's see how the bones get longer, right? So keep in mind that in the long bones there are three regions. We talked about the epiphysis, which is at the end of the long bones, and then diaphysis is the middle region. So I've got a plot here. We have epiphysis on either side, and you have a diaphysis in the middle. And in between the epiphysis and the diaphysis is the region called as a metaphysis, shown here. All right, and this comes off because the metaphysis has only cartilage in this case, and so it could easily come off. And we'll come back to this in a minute, right? So notice that in this metaphysis there are different zones you're going to see, and the part of the metaphysis which is towards the epiphyseal region, right, towards the end of the bone, that's going to have cartilage being formed. And towards the diaphysis, we see that cartilage is going to be ossified, meaning it will be replaced with bone tissue. So what you see here in this right hand panel is just a zoomed in version of what you would see in the metaphysis. So we're going to start all the way at the reserve zone, which is closer to the epiphysis, and work all the way down to the zone of ossification, which is towards the diaphysis. Alright, so keep in mind that towards this end you have cartilage formed, and towards the other end you have bone being produced. So let's see what happens in each of these regions. So in the reserve zone you have small chondrocytes which will produce the surrounding matrix, and what you see here is hyaline cartilage. And these chondrocytes, they don't really play a role in bone growth, but they're going to just bind this epiphyseal plate to this bone tissue, right? And that's the goal of this region. But then as we move from the reserve zone down into the proliferative zone, notice that the chondrocytes found here, they're going to be larger, and the reason they're larger is because they have you have multiplication of these chondrocytes. So you have mitosis taking place here, and so you have a proliferation of chondrocytes, and they're going to be stacked like coins. And here is something I'm reminded of. Right? There was a question in the RPA2 that said, why is cartilage avascular? And one of the options is that why is cartilage not capable of regeneration? And the options were it's avascular, it cannot proliferate. So based on what I just told you, do you think chondrocytes can proliferate? Yes or no? They can proliferate through mitosis, right? But what does the word avascular mean to you? No blood vessels, right? No blood supply. So the reason why cartilage cannot regenerate is because of a lack of blood supply and not the fact that it cannot proliferate. So I was made aware of that question on the group me chat, and I just wanted to address it in class. Okay, so from the proliferative zone, we see that the chondrocytes have just multiplied, but then those multiplied chondrocytes, they're going to start getting bigger, and that's what we mean by hypertrophy. So they get older and larger, and we see that the more mature chondrocytes are going to be closer towards the diaphysis, the less mature ones are closer to the epiphysis. So they're just moving downward and getting mature. So just a side note about the difference between hypertrophy versus hyperplasia. So hypertrophy is when individual cells get larger. So if you go exercise and you're lifting weights, the muscle cells get larger, and that's called hypertrophy. Hyperplasia is what happens when you have cancer, where there's going to be multiplication of cells. And we talked about cancer, skin cancer, and the multiplication of cells is hyperplasia, and the unregulated multiplication of cells leads to cancer. So moving from the zone of hypertrophy, we reach the calcified matrix. Here's where you have calcium entering into the matrix, and it can eventually cause the cells here to die. And as the cells die here, we see that the capillaries from the diaphysis can invade into this region of degrading tissue because the cells are dead. And the capillaries will not only bring in blood vessels, but they're also going to bring in osteogenic cells, which can be converted into bone tissue. And so this leads to the zone of ossification, and this will connect the epiphyseal plate to the diaphysis. Right? And keep in mind that as the individual is going to mature, you see all of the cartilage which is found at the ends of the long bones in the metaphysis and the epiphyseal region will be replaced with bone tissue. So longitudinal growth will stop only when all of the cartilage has been replaced with bone tissue. So coming back to this femur here, so this is actually the femur of a heifer. Right? So it's a cow which is not yet had a calf, 18-month-old heifer. And notice that the reason why the epiphysis can come off is because the cartilage was not ossified as yet. Right? But on the other side, you'll notice that the cartilage has been ossified. You can still see some regions remaining, and that's why there's a gap here if you were to take a closer look. But in general, most of it has been ossified, and so it's still stuck to it. Right? Any questions at all? Yes?
Where did that come from?
Someone gave it to me. Yeah. But it came from a heifer, right? Yeah. 18-month-old heifer, that's what I was told. So now let's talk about how bones grow in diameter. So right now we talked about how bones grow in length. And I want you to focus on this figure here. Let's take a quick look at the left hand panel. And this is bone growth before remodeling. And you'll see that this blue part here is showing the epiphyseal plate where there is still hyaline cartilage. And if you notice the note here, it says that the bone is going to grow in length when you have endochondrial ossification taking place here, where the chondrocytes will eventually be replaced with bone tissue. That's how you have the bone growing in length. But when you have the bone growth happening widthwise, the diameter is increasing, that is called appositional growth. And let's see how this happens by looking at the right hand panel. So notice that this is showing you the bone after it's grown, so you see it's much longer here. But also notice that the widthwise, also the diameter has increased. And this dotted line here is showing you what the bone shape was before the widthwise growth of the bone took place. So in order for the appositional growth to take place, two things need to happen. You need to have the medullary cavity increase in its diameter, and also the thickness of the cortical bone or the diaphysis also has to increase. Right? So two things need to happen. The diameter of the medullary cavity increases, so does the width of the cortical bone here. So in order for that to happen, two different things need to take place. The first one is osteoclasts will remove the tissue in the medullary cavity and thereby making the diameter bigger. Right? So the osteoclast will remove bone tissue and make the medullary cavity bigger. Whereas we see that osteoblasts are going to put more bone tissue under the periosteum. So periosteum is the outer fibrous tissue which covers the long bone, and you have intermembranous ossification happening right under the periosteum, and that's how the width of the bone is increasing. Is that clear, folks? There are two different mechanisms. I know intermembranous ossification wasn't underlined in your slides, but just please underline it and make sure you understand how endochondral ossification and intermembranous ossification play a role in the development of the bone after both. So just to re-emphasize the point, the diameters of both the diaphysis and the medullary cavity will increase, but they increase through two different mechanisms. One is through the action of osteoclast, the other one is through intermembranous ossification. Is that clear, folks? Okay, in that case, let's look at this poll everywhere question. Which type of cell do you think has the longest cell lifespan among these cells? Osteoblast, osteoclast, osteocytes, or osteogenic cells? Okay, I've got your answers. Most of you said osteocytes, and that is correct, right? So, we will move on to talk about some of the functions of the skeletal system. Alright, and I want this to be a bit interactive. I'll tell you one function, and then you can tell me what type of bone will help in that function. So, one of the major functions is to help with support, right? There's a saying: if you don't stand for anything, if you don't stand for something, you will fall for anything, right? So without the skeletal system, we would be like jellyfish, right? And let's say you're in the gym doing bench press, right? Haven't done this in a while, but let's assume you're doing this, right? When you're holding the weights above you, what bones do you think is offering support and stability and preventing the weight from falling down? No, I'm looking out the wrist. It's providing support. What bones are those?
Short bones.
Short bones, yes, thank you. And then when you're actually trying to move the barbell down and push it back up, the movement is possible because of what type of bones? Long bones, excellent, alright. And when you're capable of doing movement, you'll even engage in some type of crazy activities like this, but no problem, because we have protection from blank bones. What bones are they? Flat bones, which protect our internal organs like the brain, the heart, the lungs, and so on. We also find that, one more thing about protection. So we find that protection from the bones will also keep certain nerves from being activated. Like, for example, the funny bone. How many of you have smashed a funny bone? Right? Yeah, pretty much everybody. Right? So we don't hurt it all the time because the bones are protecting us, right? But we find that even in the radius and ulna in our hands. It's going to protect what is known as the median nerve, and that's why the Romans came up with crucifixion, where they drive spikes right through it, and so it's a horrific way of killing someone. But anyway, that's just to tell you how to appreciate how your bones protect you. We also find that bones play a role in the storage of minerals, like the calcium levels are maintained in the body, phosphate levels, and if those levels are low, we find that the bone will be resorbed and the calcium can be released into the bloodstream for engaging in other activities in the body. We also find that it can be a source of energy storage because there's a fat tissue in the bone marrow, which makes it tasty as well in various cuisines. And the bones also play a role in hematopoiesis because the red bone marrow is where you have different kinds of blood cells being synthesized. I wouldn't hold you responsible for this complex picture, but I want you to say, wow, how complex it is, right? That's all. But we'll talk about a few aspects when we discuss the blood and the immune system as well. We also find that the bone can play a role in endocrine function, and so there are hormones which can be released by cells in the bones, and this picture should make sense when we talk about the endocrine system, right? For now, just know that the skeletal system can have endocrine function as well. We also find that there's the osteoclasts I mentioned previously. They are made from immune cells, so osteoclasts can also have an immune function, right? And one of those things is it can present antigens. So we'll see what antigen presentation is when we talk about the immune system, but just know that osteoclasts are capable of antigen presentation, right? And as you know, this slide is not in your handout because I won't hold you responsible for that, right? That's why I left it out of your handout. So moving on, let's see how bone remodeling takes place. So bone remodeling will take place in what is known as a BMU, or the basic multicellular unit. And as the name suggests, we see that there will be a number of cells involved in this BMU. And bone remodeling takes place in a number of stages. So the first step is origination, where you have damage to the bone. Maybe it's a microfracture because you've been exercising, and that's the first step of origination. And then you have activation, where different kinds of cells are going to be brought to the site of injury. So this could be the pre-osteoclasts coming to the site of injury, and there they can turn into osteoclasts. Then you have resorption, where the injured bone tissue is going to be removed, and then there will be the osteoblasts laying down fresh matrix, or the osteoid. That step is called formation. And then eventually the uncalcified matrix, or the osteoid, will be mineralized when calcium is incorporated into it. And that is the last step in bone remodeling. So we will spend a little more time talking about these various steps. But before that, I have a question for all of you, right? You see that osteoclasts have a primary function. And what is the primary function of osteoclasts? Bone resorption, right? So what organelle do you think would be present in osteoclasts to help with bone resorption? Would it be the nuclei, the proteasome, lysosome, or Golgi apparatus? Okay. So most of you said lysosome, and that is correct, right? So what is present in lysosome which can help the bone tissue to be removed? Starts with the letter A. Acid. Thank you. Thank you very much. Right. I won't be there to give these hints in the exam, so just a heads up. So now let's talk about the various steps in bone remodeling. Right? So what you see here in green is the trabecular tissue, and the purple area surrounding the trabecular bone is the red bone marrow, right? And notice that there are these lining cells shown here in pink. These are the osteogenic cells, which can eventually turn into osteoblasts. And we find that there's going to be a coupling between the action of osteoclasts and the osteoblasts to have bone being remodeled. So I told you that the very first step in bone remodeling is origination, and this white line here is just showing you microfracture. And when there's a damage, it's going to activate different factors in the body. An example of that is TNF. It's tumor necrosis factor, which we'll talk about in the immune system. I already talked about IGF very briefly when I talked about acne, right? So I said if you have too much dairy products, that can increase IGF-1 activity, which in turn will activate androgens, which in turn will cause increased sebum production. So we talked about IGF-1 briefly. IL-6 is interleukin 6. That's a type of inflammatory factor, right, which is produced by the body. We can revisit what interleukins are in the immune system. PTH stands for parathyroid hormone. We'll talk about it later this week in the endocrine system. And 125D is the other name for the active form of vitamin D. Can you tell me what is the active form of vitamin D? Calcitriol. Yes, very good. And so all you need to know from this slide is that different factors are going to be recruited during the origination phase, and they can play a role in bone remodeling. I won't tell you to memorize these names and regurgitate it on the exam, but just be aware these are factors and names we will see in the future. So once origination takes place, during activation there are different cells coming to this BMU, right? And so notice that these two yellow structures, they are representing pre-osteoclasts. And these osteoclasts, they are going to have a receptor on it known as the rank receptor. And this will be bound by a ligand called the rank ligand. The name isn't too creative. Rank receptor is bound by the rank ligand. And once the rank ligand binds to this rank receptor, notice that the pre-osteoclasts can fuse together and they can form osteoclasts as shown right here. Right? And these osteoclasts, they will release their lysozymes, and thereby it will just cause bone resorption right here. It looks like the place got nuked, right? But what's happened is the damaged bone tissue and the surrounding area has also been resorbed by the acids. And then notice that the lining cells will just line this pit of resorption, and then you have osteoblasts, which will produce the osteoid, and that osteoid can eventually be calcified, and that's how mineralization takes place. And notice that if any osteoblast was trapped during this formation and mineralization process, it will turn into an osteocyte. Okay? Any questions at all to this point on the steps involved in bone formation, bone resorption and formation? Yes?
This is all just the same kind of bone that regenerates with. Is there any kind of chemical difference to it, or is it just...
This is how bone would regenerate if you have like a damage in compact bone or spongy bone. Yeah.
The new bone's exactly the same as the old bone?
Yeah.
Okay.
Yes. It actually, when you have a fracture, the amount of bone which is produced after a fracture is going to be more. So the bone is always stronger than it was. And I didn't get into the details of how a fracture heals, but I'm talking about a microfracture because that's something which we experience more during exercise, and that's how the bones get stronger. Yes?
Yeah, does this apply for like a more compound fracture or something larger as well?
That can be a little more complex. You have bleeding and all of other factors involved, inflammation. So that would be different. That this is more for bone remodeling and for strengthening the bone. Yes.
I was going to ask, is the osteoid kind of like a scab of the bone? It's protecting it so it gets warm.
So the osteoid, is it acting as a scab? No, it is the precursor to the calcified matrix, right? So the osteoid is the matrix before it gets calcium incorporated and it gets hardened. Yeah. Great questions, folks. Anything else? Yes.
How is it recruiting these factors?
How is it recruiting these factors? questions way beyond the scope of our discussion. We can discuss this offline. But great question. Okay, so all of these steps I just now said, I have it in text form for you. If you want to go back and review what I said, and if anything wasn't, if you thought you missed something, please look at these notes here. So what I'll do now is I'm just going to quickly go through this animation one more time in a little faster rate so you see how this all happens. So microfracture and get new bone forming. Alright. So moving on, which do you think is the master regulator of bone remodeling? Among the different types of cells in the bones, which do you think will regulate bone remodeling? Is it osteoblasts, osteoclasts, osteocytes, or osteogenic cells? Okay, got two answers. Most of you said osteoblasts. So the master regulator for bone remodeling is actually osteocytes. The answer is C, and I'll explain why that is the case. So I hope this cartoon will just drive home the point. So it says osteocytes. So this is the cell shown in the middle with all the spiky hair. But notice in his hand it's got a go sign and a stop sign. All right. So this is denoting the osteocytes, and it's going to coordinate the activity of osteoblasts shown here, building the bone tissue, and on the other side you have osteoclasts, which is shown by a bunch of bulldozers trying to destroy the bone tissue. Now the way the osteocyte determines whether the osteoblasts do their thing or osteoclasts do their thing, it's by these factors: rank L, OPG, rank L, rank, or SOST, right? So what does all this stand for? I'll tell you in a second. So OPG stands for osteoprogerin. This is something which is produced by the osteocytes, and when OPG and rank L interact, it will promote osteoblast activity, right? So what does rank L stand for? It stands for receptor activated for nuclear factor kappa B ligand, right? I will never ask you what rank L stands for. This is here for your curiosity's sake. And this rank ligand will bind to a rank receptor, and SOST standing for sclerostin, right? So what are all of these things? Let's take a closer look at the at this next figure here. So this is showing you the rank L, OPG system, how they're all modulated by the osteocytes for either bone formation or bone resorption. So this shows the osteocytes here, and they have the various dendritic projections from them, and they are the ones which will produce all these three. They can produce the rank ligand shown here in dark blue, they can produce the osteoprogerin shown here in light blue, and they can also produce sclerostin shown here in is it magenta? Magenta sounds good. All right, great. All right. So we find that if the rank ligand, right, binds to the rank receptor on the pre-osteoclast, you will have osteoclast made. Alright, so this cartoon just shows the rank receptor on the osteoclast, but I told you previously the pre-osteoclasts have rank receptors, and if you have rank ligands binding to the rank receptors, you have osteoclasts being produced. So we see how rank L rank interaction leads to osteoclast production. So the one way I like to remember this is, if you want to be ranked, you have to be classy. Alright, so rank L interaction leads to osteoclast synthesis. So if anything can impair this type of interaction between the rank L and rank, that can cause bone formation, right? So that is possible due to OPG, which is also produced by osteocytes. So osteocytes will produce OPG, which will bind to the rank L, and now the rank ligand cannot bind to the rank receptor, right? And so that can lead to bone formation. And lastly, notice what sclerostin does. Sclerostin is also produced by these osteocytes. It blocks the existing osteoblasts, and it will activate the osteoclast. Right? So sclerostin is going to be released by osteocytes. It will block the osteoblast activity and it will activate the osteoclast activity. Okay, so why did we talk about all of this? How does this relate to having either too much bone or too little bone? Alright? So let's talk about what is the consequence of having too much bone density. So this is an article from the Journal of New England of Medicine and the New England Journal of Medicine, sorry. Yeah. And so this talks about a mutation which will affect a protein which is supposed to interact with sclerostin. Right? So we see that sclerostin is going to antagonize the pathway for bone formation. So sclerostin will prevent bone formation. And sclerostin is going to bind to this lipoprotein related receptor related protein. So it's called LRP 456, right? So all you need to know is that if you have a mutation in this LRP, that's going to prevent the sclerostin's pathway. And so as a result, we will see an increase in bone density. I don't need to remember this, what LRP stands for, but just keep in mind that sclerostin has to bind to something, and that protein to which it has to bind has a mutation, and so the downstream effect of bone density will not be decreased but increased. So let's see what happened to a family in Connecticut where they had this mutation. So the first picture here shows the face of a 12-year-old girl. Notice how her jawline is, right? And this is her relative who's 45 years old, and notice how thick the mandible is, or the jawbone. And also inside the mouth you have extra teeth because of this mutation. Right? And another thing we find from from decreased osteoclast activity is that the bone marrow, the medullary cavity within the diaphysis is pretty narrow. I told you that for appositional growth, the diameter of the medullary cavity increases through osteoclast activity. So it makes sense why the medullary cavity is very narrow in these individuals. And also the vertebrae is going to be pretty dense if you look at the X-ray. So the consequence of this is that it can affect your ability to stay afloat in water and also to swim. So is this clear why having too much bone density can be detrimental as well? Any questions at all? Yes?
Does it also make the bones stronger?
It will make the bones very strong, yes. So you can, the one problem which these individuals won't have is osteoporosis or fracture in bones, yeah. But the bones will be very strong. Yes?
So I was going to ask, since they have like mouth teeth in their mouth, right? So I guess the marrow has to go somewhere else, like it has to be distributed there instead of like their leg, it looks like.
So the question is, would there be lesser marrow in the diaphysis? Yes, absolutely, lesser marrow. And I'm not sure what the outcome of that is. You know, what are the consequences of having lesser bone marrow? Yes, you believe you had a question too.
How does this result in extra teeth? Why does that have a dental?
I mean, the teeth is also made up of calcium phosphate, right? And so, not sure what the pathway is in that, but it's seeming to result in extra teeth in abnormal regions as well. Yeah. Anyway, but this is not as serious to the quality of life as what we consider next, osteoporosis, right? So we find that while we're younger, we have higher osteoblast activity, and we have less osteoclast activity. But when you get older, your osteoblast activity is going to decrease, and the osteoclast activity increases. And as a result of this, let's see how the bone calcium is going to be affected as we age. So on the left axis, on the y-axis, we find bone calcium is shown here, right? And we find on the x-axis there is the age change, right? So while we are born, and then as we get older, up to the age of 25 or so, notice that the bone calcium is going to increase. And the reason is this because of intermembranous ossification and endochondral ossification. Calcium is being incorporated into the bones, and so there is increasing bone calcium levels. But then after you stop growing, we find that the osteoclast activity generally starts getting greater, and the bone calcium gradually decreases. Right? And this is the curve you would see in males. But in females, you notice that there's a more dramatic drop as you age because of menopause. So if there's menopause onset, then estrogen isn't being produced, and that seems to somehow affect the osteoclast activity and increase that. Right? So that means that you're going to be closer to the breaking point, and that increases the risk of fractures. Now, as you age, you notice that this is what the normal vertebrae looks like, but then as you age, we find that the bones on the inner side of the vertebral column, they seem to be more susceptible to loss of calcium, and that's why it leads to this dowager hump as you get older. Right? So we see that the long-term loss of calcium from the bone is this condition called osteoporosis. So what does this look like when you look at the microarchitecture of the bone tissue? So this is a normal bone. Notice how thick the trabeculae are. But here, when you have osteoporosis, you see the bone matrix has become very small, and even a small fall can cause a fracture. Right? So we see that it's going to increase the risk of fracture. So the definition of osteoporosis is the progressive systemic skeletal disease characterized by low bone mass and microarchitectural deterioration of bone tissue, and thereby it will increase the susceptibility of bone fragility and make it more susceptible to fractures. So the way they determine the osteoporosis score is by doing a bone scan, and they come up with a value known as the T-score. So they take the bone density of people in a given age group, and then they do a normal distribution, and then seeing how many standard deviations you are away from the normal distribution, you get assigned a T-score, which will tell you whether you are at a risk of osteoporosis, or if you already do have osteoporosis, and if it will increase your risk of bone fractures. So both men and women are affected in this, and 1 in 3 women over the age of 50 will experience a radial fracture, whereas in men it's between the 1 in every 5 will experience this. So this can significantly affect not only the quality of your life. If you are immobilized, that's going to affect what you can do. But many times for elderly people, once they suffer a fracture like this, it can also decrease their lifetime. It could be a point of no return, if you don't have a strong enough support system to help them recover. And the annual cost is close to 19 billion, and this will only increase in the years to come. Right? So what are some of the ways in which we can decrease the risk of osteoporosis? So one of the ways in which that can be done is by engaging in weight-bearing exercises. Right? So when you engage in weight-bearing exercises, let's assume you enjoy yourself. Right? The question I have for you is, if you get immobilized, how much bone density would you lose on an average within the first year of being immobilized? So do you think it's 10%, 20%, 30%, or 50%? Yeah. Most of you said 30%. You seem to be a bit optimistic, but I need to burst your bubble and say that it's actually 50%, and let me explain why. So in this graph here, notice that it's showing the change in bone density on the y-axis, and on the x-axis you have time shown. So if you are engaging in just walking, right, alone, you're going to walk into class and back, and no other exercise, you can increase your bone density by around 5%. But let's say you engage in heavy weight-bearing exercises like running or weightlifting, and swimming doesn't cut it because you're in water, you're buoyant, and you're not putting pressure on your bones. You can increase your bone density by around 10% by engaging in high-impact activities. But then if you aren't being active and you're immobilized, notice how dramatically the bone density drops off, and that's why I said you can lose up to 50% of your bone mass when you're immobilized within the first year. So how does the bone sense that the more you exercise, it needs to maintain the bone density? So keep in mind that these osteocytes, right, they're going to be mechanosensors. So they'll be floating in the interstitial fluid in the laconium, and the interstitial fluid is not capable of being compressed. And so when you put weight on the bones, the stress is detected by the osteocytes, and it will pass on the message to the surrounding osteocytes through the caniculi and the connections to the gap junctions, and that's how you have osteoblasts being activated to eventually generate bone tissue. And we see that all of these interconnections are important for how stress-related action because of exercise can be communicated from one cell to the other. So by engaging in more exercise and having adequate calcium in the diet, we can increase the amount of bone density while we still have high osteoblast activity when you're younger. And then once the age-related calcium loss takes place, you are still further away from the breaking point. Right? Keep in mind that this graph here is a bit of an exaggeration because I told you that heavy exercise can only increase your bone density by 10%, but I hope you get the take-home message, all right, from this, that by exercising and having an adequate diet before you get into your 30s is a good idea. Let's talk about some of the risk factors of osteoporosis. We know that low estrogen levels caused by early menopause can be one cause. And so one way to treat this is by having estrogen replacement therapy. We also see that eating disorders in teens and preteens can also decrease how much calcium is incorporated into the bones. And just having a smaller body frame means that you have less stress on your bones, and that's going to not provide the signals to your osteocytes for maintaining the bone density. And if you have a genetic history of having osteoporosis in your family, regardless of the lifestyle changes, you would need medical intervention to decrease the risk of osteoporosis. Early malnutrition will have the same effect as eating disorders in teens or preteens, because when you have high osteoblastic activity, that's when you want to get calcium incorporated into your bones to the various extent. We also find low vitamin D levels will affect how much calcium is being absorbed by your small intestines and thereby incorporated into your bones. Some medications like prednisone and other anti-inflammatory drugs, they can also increase osteoclastic activity. And any sort of pathology in your small intestine, like celiac disease or inflammatory bowel disease, all of that will affect how much calcium is absorbed from your diet. And finally, if any of you decide to go into space, keep in mind that just getting off planet Earth is going to decrease your bone density, because staying on Earth and having the gravitational force acting on you will retain the bone density, right? And so if you are an astronaut, expect to work out at least a couple of hours every day doing weight bearing exercises, so that when you come back to planet Earth, you will have sufficient bone density for your activities. So to summarize, we talked about bone growth after birth is going to happen longitudinally through endochondral ossification, and acquisitionally it will happen through intermembranous ossification. Keep in mind that the functions of the skeletal system include a number of things, and it also includes endocrine regulation. And we talked about the bone remodeling happening through the activity between these rank L, rank receptor interaction, and also the OPG, which is produced by osteocytes. And in terms of pathology, we see that there's increased bone density that can prevent you from floating, and you have a narrow medullary cavity. And if you have too little bone density, that can increase your risk of osteoporosis. All right. And these are the key questions I hope you can answer after listening to the lecture. And I'll see you back on Wednesday. Thank you all for your time. care.